We'll do some like,
I'm not sure.
what's what?
Like that.
Like when you
So,
yeah, things like that. It's really fun.
If you're doing Node, have you looked into Dino or Deno or however you like to pronounce it?
A little bit. There's not any advantages that make it worth going greenfield right now. So,
Discord, make it simpler.
but it is interesting.
That's when, like, if you have the server invite, I might be able to just
I imagine once it
Oh,
matures,
yeah,
it
yeah,
will.
yeah, I do have that.
sense clearly friends it's not
Yeah.
okay. Awesome.
I feel like you're the Wizard of Oz. Like you can see you typing, but there's nothing on the screen.
Oh yeah, sorry. So that's because I'm just getting, I've got it broadcasting now to YouTube and Twitch, and I'm just getting the comments up, so in case anybody pops in,
There you go.
Awesome, thank you.
I can see that too. Okay, there we go. All right, now we've got everything half working. I think half working well enough to get started. So, thanks for bearing with me. I'm not the person that should definitely be doing more than one thing at a time. I should either be the pizza guy, or the meetup guy, or the presenter, but not all three at the same time for sure.
Can people on the internet hear us? Sound check. Are they all?
I can hear you.
Okay, you can hear us.
All right, cool. I'll check one more thing actually. Thanks for bringing that up. Yeah, okay, this is connected. Cool. All right, well. So again, first of all, my name is AJ O'Neill. I am Rust curious. I run the Rust meetup, but it's more out of happenstance than out of expertise. I really think it's a great a language and opportunity, and I am following it so that I can ride the wave, much like I did back in the old Go days. I wasn't actually a big Go person at first, now I am, but I kept watch on it to see where it was heading and what was going on with it, and knew that it was, coming any day, and then it came, and that's been awesome. Anyway, so I'm familiar with Node, I'm familiar with Go, I'm a little bit familiar with Rust, but we're going to let the experts or beginners that have more experience than other people in the room chime in as I say things wrong.
Yeah,
And
only Levi's an expert.
well, Levi, yes. Levi is an expert. Unfortunately, he is not here today. But we're going to go over concurrency models. And this is actually going to be pretty simple and straightforward in terms of, we're just going to talk about a few of them, and then it's going to be Q&A. So most of this is going to be Q&A. With all that out of the way, this is supposed to actually be slides, but something didn't go quite right, and so it's showing up as a markdown file, which is okay, I guess. So I'll just scroll through this. Anyway, slide 1, all the concurrency models of the rainbow. Yay! First, what is not a concurrency model? So I want to make sure we're all clear that if something is blocking, if it's single-threaded and it's blocking, it is not concurrent, and that is the definition of not being concurrent. And if you've ever used Python, then you are or Ruby, then you are familiar with the terribleness that is. This is how you construct the same terribleness in Rust. You could attach a listener to an address, and you could just iterate over each stream that's incoming. And what you would be able to do with this is handle one stream at a time. So as long as you are handling the one stream, you are not handling any other stream. So this would be single file. This is the Walmart model in the worst possible way. This is everybody's in a single file line, and there's only one register, and you are sitting and you are waiting for the register to be available. And the whole time that the person in front of you is unloading their cart and getting items scanned and everything's going on, you are doing absolutely nothing. You are sitting there waiting. That is the blocking model, the old terrible way that lots of things worked. And there's all sorts of Apache mod this and that, because Apache would handle the threading model and the programming language would be running separate entire copies for every single visitor. It was badness. Then the next thing, which would be its own slide in nice large print here, would be concurrency versus parallelism. So we know what is not concurrent, what is not parallel. But the other issue is considering the difference between concurrency and parallelism. So I'll give you something that is only concurrent and something that is only parallel. So if you have a for job and jobs, I'll take a bite while they're getting in the door there.
Sorry, I got a seat down there as well.
Hey!
Oh, it's the other expert.
We left you some
We're
pizza.
staying.
I was playing with weave. I'm like, wait a minute. This is not the weave address. Oh crap! It's way far away.
Another 22 minutes, yes.
We
Which is
also
why
got more sticker variants.
We got food here for you.
Oh sweet. Yeah. Good, because I have my dinner. Do I need to chip in? Yeah.
$5 would be great.
All right. I'll do it.
We can do that after, yeah.
He takes cash for electrons.
Cash
Oh.
or electrons.
Okay, so if I'm doing something in parallel, it's typically I'm doing the same thing. That's what we're talking about. So I'm batching many different things. So we take the Walmart model where there's one register, and now we say there are 4 registers. So there are 4 lines of people standing in line, waiting, unable to do anything while they just stand there and wait. But there's 4 lines, so we can go through it faster. And then there is...
Do we get to quibble about the pros and cons at this point? You might go through all the bottles first.
I want to go through all the bottles first.
Okay.
And then let's quibble about pros and cons. So then there is concurrency means essentially that something else can be done while nothing is being done. So this is a JavaScript example, a front-end JavaScript example. Imagine you had a bunch of buttons on the page, and each button has an event listener that is a click listener. So if we had these 10 buttons, you could press any single button, and that button could do an action. So I could press the first button, and then I could press the 5th button, and then I could press the 2nd button. So I can press the buttons in any order. I don't have to wait for button 1 to be pressed in order to press button 2. There's no backlog. Each button can listen to a click, and each button, when clicked, can do something. However, in this particular case, only one thing can happen at any given time. So if you click button 1 and button 1 has to go do something, while it's doing that thing, you cannot click button 2, or if you try to click button 2, there will be no response because it is the web thread is not yet ready to respond to the next thing you want it to do. Now, in the case of a button click and doing something like console.log, you wouldn't be able to hit 2 buttons fast enough for that to have any effect. But let's say that you had a loop that counted to 100 million. That might be slow enough. I think 100 million would definitely be slow enough that it would halt the thread and you would not be able to click on button 2.
Waiting for a database query.
Well, but that in JavaScript does not calculate because JavaScript is concurrent by default. So that would put you back in a wait state.
Yeah.
But yeah. So any questions about blocking, concurrency, and parallelism? Because if we understand that, then we're in a really good place.
So we're using parallelism in the sense of multi-core and concurrency in the sense of async await.
Yes.
Yeah.
Yes. But you can mix and match these. You can also do things in parallel and concurrently. And so, for example, in Node.js, you actually do get, I wouldn't call it parallelism, but you get multi-threaded because the threads happen on the back end. So when you do that database query, the thread that's handling that network request is happening. It's just happening in a place where you don't deal with it. So there can be as many database queries going on at a time, but the main thread in Node.js can only do one thing at a time. If you have a JSON.parse or a JSON.stringify, console.log, JSON.parse, JSON.stringify are the three top things that make Node not be able to handle a sufficient number of requests, because those are the things that take up a lot of time that people don't realize they take up a crap ton of time. And they scale really, really badly. So you do a small JSON.parse or JSON.stringify, you won't notice it, but as you linearly increase the size of your payload that you're stringifying or parsing, you're exponentially increasing the time that it takes to process it. So it can be really, really efficient for, say, if you want to copy a small object, there's probably no more efficient way to copy a small object than JSON.stringify, JSON.parse. But if it's a large object, then it becomes very, very inefficient very quickly.
I mean, for the button example in browser, you could also use web workers, right, to get some sort of concurrency so that other things can happen.
Yes, so if you wanted a web
Right.
worker that counted to 100 million, you could click the button and you could put that in a web worker, and that is essentially a thread. A web worker is about as close as we get to threads in JavaScript.
So is anyone here old enough to remember cooperative multitasking on Windows 3.1 or Mac OS?
What did you say the name of it was?
Cooperative multitasking.
I don't remember that.
I don't know by that name, but I believe I know what you're talking about because I'm familiar with
I
it.
just feel like everything old is new again, because concurrency with everything going on in your app was that in the main message loop you said wait for the next event. It at that point is yielded up potentially for the operating system to potentially have some other program that assigns the CPU time to do something. But if you were doing lots of stuff in your thread, everything else would be on hold until you said, okay, wait, next event.
Yeah. So,
That I mean, there wasn't a CPU processing power to have a multi-threaded operating system. The overhead was too high. So the advantage of this thing here is that the blocking operations are more naturally turning things over than that one call of wait next event that you had working in Mac or Windows.
yeah, and I think
You have to be a good citizen when running an app where you bring everyone else's app to a halt.
Well, I think back at those days, the other problem was we didn't have multi-threading yet anyway, because that was introduced with the 386 or the 486.
Well, the 386 made it feasible to do that, really, but the operating systems lag behind that. But like the concurrent one, even on a single thread, it's very low overhead to handle those multi things compared to the overhead of. There is a price that you pay for running multiple threads
Yes. Okay.
if you only had one core.
Well, regardless of how many cores you have, there's a price you pay.
The more the threads have to contend for any course, it's
The whole issue of copying the stack to memory and pulling the stack down, you weren't doing that in a concurrent system like Node.
Okay, so then this was supposed to be just a slide that says threads. At which point, I would say what I'm going to say now. With threads, you're essentially dealing with what is a task that can run on a CPU. A thread has, so when you start your program has one thread. And that thread has a call stack, which is basically the variables that you're using in any given function that aren't being shared between many different functions. If you're coming from the Node world, that is kind of what a call stack is. So in the Node world, you don't really know about the stack and the heap because it's all just kind of magicked away. But the optimization is basically this. If a variable stays local to a function and doesn't get assigned as a reference to something that's in a different scope, then it will go on that function's stack. And if it is the opposite case, it will go onto the heap. And in the olden days, if you think of a stick of RAM and it's got chips on the stick of RAM, the stack would fill from the bottom, and every time you call a function, it would create more stack space for that, and every time a function completed, it would pull down the stack space. And then the heap would start from the top, and the heap would be all of your large objects or things that you want to keep around for a long time. And back in the olden days, things would crash because the heap could get fragmented and you couldn't make allocations anymore. But we don't have that problem anymore because we've got computers with over 4 gigs of RAM and better allocators. And in Rust,
You just haven't written big enough programs.
Yeah.
well, do you? But wait, do you still is heap fragmentation still an issue on modern computers?
Yes.
So it could still happen that you could
Especially in
have.
big games when you're doing your own slab allocation.
Okay. Yeah. So the thing that I heard about this being a problem was War Stories, Ars Technica War Stories. I'd have to pull up the episode, but they were talking about how they basically were never able to launch their game because they hit the 4 gigabyte virtual memory restriction, and no matter how much they optimized, they could have, say, 50% or 60% of the RAM free, but they couldn't allocate any more RAM.
Poorly fragmented.
The worst case scenario is that you've got small heap allocations mixed up with large heap allocations. So you might have 4 gigabytes free of RAM, but unfortunately you need a 4 gigabyte chunk and you have a 10 byte allocation right in the middle of it, so there's no continuous segment on there.
Mm-hmm.
In the old days, you used to have handles to memory, so the operating system had a way of sort of redirecting the memory under you to make all that work. But it is still an issue.
Yeah, but to your point, it's not as bad as it used to be.
That's right. You have to be in that
You have to work
1%
it
of weird stuff to worry about it.
So for most software nowadays, you probably would never run into it unless you're building a game.
Unless you're building your own engine for your game.
Scientific computing a game, something with huge amounts of data working at the same time, most web transaction stuff, no.
Right.
Machine learning, some big ETL there.
So, in any case, you can think of the stack as something very clean and very fast that's relatively small, and it's like a stack of books. Like every book you put on the stack, you have to take a book off to get down to the book beneath it, whereas a heap is more like a bookshelf where you can take off books and put them in any order, and if you need to put in an encyclopedia volume, but there's the never-ending story in the way, then you can't fit your encyclopedia volumes in that space on the bookshelf because you can't get the contiguous space in order to allocate. So that's one of the problems with we'll just heap and stack, and that really applies to everything. But when you have threads, each thread has its own stack. For all intents and purposes, each thread is its own program. And so it has its own stack. It has, I guess they share the same heap, but it takes up a lot of space. And there's this concept of context switching, which is that anytime a CPU needs to switch between threads, especially before what they now call hyperthreading, which is just that you can switch threads really fast. You can basically queue up the thread that's going to run next on the CPU ready to go, and then the CPU will switch between two threads very, very quickly. But still, it's a problem. It's called context switching. So you have a lot more memory that you're using when you use threads, and it's a lot slower because every time you need to switch between tasks, the CPU basically has to say, okay, I'm going to take this chunk of program that I'm running, I'm going to put it on pause, I'm going to go put it in cache, or throw it away for now and get it from RAM later, and then I'm going to take this other program, and I'm going to load it, and then I'm going to start running it. And so if you have 1,000 threads, and each one of them is a web request, and they each need to do small little things, then you get thrashing of the CPU, where most of the time that the CPU is spending is loading and unloading threads rather than doing the work. So the CPU can be very efficient at doing these tasks as long as the programs are not written super, super inefficiently. But that's...
You could also run a RAM, just from the stack. Like the 10,000 connection problem. So, what is it, 8 megabytes per...
Depends on your OS. 2 megabytes is really common. It's configurable.
Yeah, but
It can be 8.
yeah, like Apache Tomcat running things that if you had 10,000 simultaneous connections, it would use all your RAM just for the stacks.
Yes. Because
Which
each
is really
thread has its
freaking
own, has a dedicated amount of stack
It
space.
uses a couple hundred.
Which is
bytes
how,
per second.
with all the virtualization of RAM and things being thrown all over the place, basically the stack is allocated contiguously, guaranteed. Oh, excuse me. And we got some people joining in from YouTube and Twitch, so hello to all of you. Thanks for joining in. Feel free to comment with questions, and I'll try to look over here. When I'm looking here, I'm looking at the comments, so I'll try to look over here occasionally and catch that.
Threads can be easier to reason about than concurrent programming. especially when the logs are involved and so forth, but you pay the price of the overhead of swapping things around in the memory footprint.
Right. So one of the things that you could do in the old school way, which maybe I'll just touch on this briefly and then move on to event loops. But the old school way is you could actually take function pointers, which again, you don't have to worry about that kind of stuff in Node land, because we've got a couple of people that are primarily Node developers tonight. You basically could take some function pointers, put them over to the thread, and then have the thread run something, and when one thing is done, have it run the next thing. And so you could have a mutex and an array and just be pushing functions over to the thread, and every time it's done running one, have it run the next one. And so this is a way that you could pool some threads, and instead of creating a new thread for every function, you can just have some mutexing logic and then push the functions to the thread. And this gives you a little bit more control in the software land to make sure that your threads are running efficiently and you have fewer threads for the CPU to switch between. And then if you take that pattern and you make it generic, that is what an event loop is, and that is what Node does. So Node has a C library called libuv, which is abstracted for the different threading models across the different operating systems. And every time you have a callback or a promise in Node for something like disk access, network access, anything that has to sit and wait, instead it will put that function onto essentially this thread pool, and it will let the threads do their thing, and the event loop will run, and whenever a function has completed, then it will queue that up to fire an event into the main thread, which is where you get your promise completion or your callback called. And that's essentially the node model, is you just being more efficient with threads. But the problem with the node model is that you only get one thread that you are in control of. All of the other threads are abstracted away from you. And this is to protect you from memory corruption, and this is particularly important in the browsers the way that they were back in the 1990s, because memory corruption is how you design worms and exploits and gain privilege escalation. That's how you take over somebody's computer, is you get some memory, you identify a chain of events in which memory becomes corrupt, and then you find a way to get your code to be where something else is supposed to be, so that a function that you've designed would basically be, imagine you precompile a program and then you ship that precompiled program into somebody's function pointer, and then the program goes to run the function, and instead of getting the function that the program was designed to run, you've replaced that function with your assembly code, and then it just runs that instead. And this is how the exploits of the world work.
Can I interject a really layman's example, just while
Yeah.
we're on event loop? So I mean, it's like if the thread is just my hand, and I want to, send this over to Pizza Land and have it do something, instead of just sitting here and waiting for it, I could also come over here and send this over to Pizza Land, and now Pizza Land can tell me, I'm done with that Mountain Dew, and so as soon as I'm done, putting this one over here, I can know, okay, let's pick up this one and do more stuff with it. So it's just a way to keep things moving along without, blocking and saying like, well, I have to wait for the Pizza Land to be done with this one, I take it back, now I put this one there, wait for it to be done, put it back. So it's just a way to queue things up and keep it moving.
I thought fast food's fast food or shorter cook, all these orders come in, could be a lot of stuff on the grill, they take different amounts of time to cook, and when something's ready, the cook says, oh, this one's ready, I'll serve it back up to the main thread to go do something with it until the next thing's ready, I'll serve that up.
Yeah, that's a good example.
Yeah, so often, what the thing that I was going to say but forgot to say is that this is what I call the Starbucks model. So you've got the Walmart model, is you've either got one and everybody's blocked, or you've got many but everybody's blocked. Starbucks model is you go up, you place your order, you sit down, you read a book, you do whatever you want to do. You're completely free to use your time however you want to use your time. And then when your number is called, then you go pick up your latte. And that is the node model. There is one register, there's one barista, there's as many, or one person taking, there's just one register, doesn't matter who's taking the order. And there's as many machines in the background as there can be, but there's only one point of entry. That's Starbucks, that's node. Now, if you go into some other models, then you get the best of both worlds, because you can take the Starbucks model and the Walmart model and say there's many registers, and you can go and sit down, and that's like the food court model, which is kind of what we'll talk about next.
So, I wanted to interject there.
What was that?
Yeah, I wanted to say something about, I think I heard you say that thread pools help reduce context switching overhead. Is that right?
Yeah, thread pools. So, well, not the thread pool, sorry. I said that the wrong way. A thread pool is technically just when you have threads that are ready and waiting. The complement to that is what the thread pool is waiting for. So if you pool threads and then you have some way of communicating what the thread should be doing next, that's where you get the efficiency. Not in the act of creating the threads, but in the act of having data ready to go into the threads and then be reused.
Right. So you still have the context switching overhead, but you don't have the spawning overhead.
Well, you reduce the context switching overhead because you can limit the number of threads to the number of cores you have for a CPU.
Sure. Yeah.
And with hyperthreading, you get 2x. So you could reserve, what I'd say you do is if you have 8 cores, you could run 15 threads, because hyperthreading will allow you to not have context switching between most of them, and then you want to reserve one just for the main loop of the application and not let it be overloaded.
Right, that makes sense.
Okay. So, next, channels. So there's channels and coroutines, and goroutines are all kind of related. Rust has channels too, but it doesn't really do goroutines. It does async await, but all the same. I guess channels are not really part of concurrency per se, but they are a way of communicating information. So back to the Mountain Dew example. So one thread is instructed to put the Mountain Dew right here, and then the other thread is instructed to put the Mountain Dew right here. Oh, I can't do it, error, right? And then there's both threads are instructed to put the Mountain Dew right here. And then you end up with 3/4 of a can of Mountain Dew, and the rest of it is in lost memory space. So that's the problem with this model is just you can tell the CPU you have multiple core CPU, so one thread can be running on the CPU, the other thread can be running on the CPU, they can both access the same RAM at the same time, and then you end up with corrupt memory. So you can imagine in the physical world we can't smash those two cans together, but just imagine we were in the quantum world and the cans just like came into each other and then they were both there simultaneously existing, overriding each other's existence.
Wait, I thought we were talking about Rust. Rust isn't going to do that to you.
Well, you can't have that happen in Rust.
generically.
Oh,
We're about to say
generic.
why you want to do it in Rust.
Okay,
Yes, so-
got it. Sorry, I apologize.
Yes, that cannot happen in Rust because of the borrow checker. If you try to do anything that would cause memory corruption in Rust and you do not have the unsafe option turned on, then the program literally will not compile.
Does Go Channels have any safeguards around that?
So Go channels, yes, and I'll get to that in just a second. Any other questions? Yeah, I'll just go into that. So with Go, the Go routines are essentially lightweight threads, pardon my French. They do the thread pooling behavior that I talked about, where every time you create a Go routine, it puts a function pointer on a stack for a thread that is available to run. With Go, you can still have that same problem of accessing memory locations at the same time in the same place. So the motto is
It's already
don't communicate by sharing memory, share memory by communicating. And channels are essentially syntax sugar over mutexes. And a mutex is a way to tell the CPU, before you attempt to write to this memory location, read or write to or from this memory location, stop and check to see if it is in use by any other CPU. So there is some overhead to a mutex. It does have to stop and think for a second. But that stop and thinking for a second prevents memory corruption. A channel is just a pretty syntax sugar to declare a mutex such that it's almost like calling a function. When you send something through a channel, it's essentially equivalent to calling a function that has a mutex lock, a data assignment, and a mutex unlock. But because there's a little bit of syntax sugar there and it has these paradigms of don't communicate by sharing memory, share memory by communicating, it helps aid people to think a little bit differently. Now, you cannot use channels in every place that you would use a mutex. It won't do the right thing. You can get mutex locks from channels. If one channel is sending and another channel is waiting, and they're dependent upon each other, you can get into a lock where neither channel can send and neither channel can receive. So the same types of problems that you have with mutex locks, you have with channels, but if you design your channels according to the Go philosophies, you shouldn't run into those errors. And there's an excellent blog post by one of those four main dudes of Go that, because there was a lot of people that started saying channels, channel all the things, and he came back and said, no, channel most of the things because in most cases it makes sense to do so. Don't bend channels over backwards to make them do things that they're not designed to do. And he outlines where a channel makes sense and a mutex makes sense, and where something else, maybe it was an atomic makes sense. And an atomic is essentially the same thing as in the sense of a channel. You tell it that you want to send data and it's like calling a function. An atomic is a variable that when you go to read or write to or from it, it is syntax sugar around the same thing, where it will lock a mutex, do the read or write, and then unlock the mutex. And mutexes you can have read-write mutexes, and you can have read-only mutexes. And the difference between the two is it generally doesn't matter if multiple things read data at the same time. Like I can look at the scan while you can look at the scan. What we can't do is we can't both write to it at the same time. We can't both place the Mountain Dew in the corner of the pizza box at the same time. So generally with a write mutex, when you activate a write mutex, nothing can be done, not reading or writing. But when you have a read mutex, it just says, hey, I'm reading this, no one can write to it, but anybody can read from it.
I like to think of Go routines or channels like Elixir and Erlang. You're avoiding the conflict from memory because it gives you a way of declaring, I'm giving this data over to you, and I'm not going to and I cannot access it anymore after that point. Once I put it to the channel, there's no way in my code I can go back and try it. Well, maybe you're a clever hacker or something, I don't know, but you're basically saying, I've given that off, there's no way for you to go back and access that. So there's not going to be the possibility of having that conflict.
Yeah. So in Rust, you're actually moving things across the channel.
Yeah.
And on Go, if you are just on a single thread, it's basically going to act like you did, right, in that case. Because it still kind of mimics that, like almost like a JavaScript generator type flow.
Yeah. So until Go 1.6, it was 1.5 or 1.6, something fairly late, Go wasn't actually multi-threaded. And then the day that they changed it to being multi-threaded, tons of stuff broke because people were writing programs that wouldn't work in a multi-threaded environment. They just didn't know that they had never been running in a multi-threaded environment. It was running like Node.
It's similar to the very first time they started putting 2 cores or 2 CPUs on a motherboard. We had a lot of C++ code that broke. Because what we had before really was the concurrent situation and not the parallel situation.
Yeah.
Without realizing it. We had designed for concurrency but not parallelism.
Yeah, that was really painful.
Boom. That was a learning curve.
I was a little bit too young, just a few years too young at the time, so I didn't experience that pain.
I was like in elementary school, so.
I didn't experience it programming, but like I remember getting my first multi-core CPU and just everything I was used to wasn't working, and like, I don't know why this is breaking. Took people a little bit of time to catch up.
Yeah.
Part of the magic of Go channels or Rust to get really high throughput in a multi-thread environment, if everyone's always waiting for the mutex,
You gotta avoid locks.
that everything runs slowly. But whether it be by the borrow checker or by channels in Go, if you can somehow declare things that yes, people actually are not going to be sharing information, so there's no need for a mutex, or if there is, the Go channels really just tiny little time to serve it all the stack and not, then you can truly run in parallel without waiting for exclusive access to memory.
Right. And that's one of Rust's promises is fearless concurrency.
And blazingly fast speed.
Yes. Faster than a speeding bullet. So then we get to the last bit here. And somebody mentioned green threads earlier, so I think we'll have to circle back and talk about that. But the last bit here, Go does not have this. Node has this, but it doesn't matter because it's just syntax sugar. It doesn't actually mean anything. And in Rust, async await is actually meaningful. And I really don't know too much about it, other than that you can have multiple event loops, and whatever pattern you pick, which hopefully nowadays would be the one that's built into the language, because I think there was like 3 competing standards in total for futures and promises and async await in Rust that were popular.
Well, we still have the issue that the syntax is built into the language, but the runtime
Yeah.
is not built into the language.
You have to pick your runtime after the fact, or like when you're
So
getting started.
they did that because so you can have competing libraries for runtimes.
But one of them now is like core Rust maintained, right? Isn't the
There's
Yeah,
a standard one,
yeah.
but like in an embedded system where I want to have the minimum footprint, part of why they did this is if I'm running a very small embedded environment, I don't have room for a lot of stuff. So by it being a library as opposed to being part of the language itself, I don't have to have that running in my embedded environment. But because it is a library, that means you can so choose to have a different runtime library. We have a bit of conflicts of versions of libraries because until this came out, there was, now we have like 3, I think. There's 2 major ones. There's Tokyo.
Yeah, you have
Tokyo
Tokyo
Standard.
Basic Standard, and then there's the IOU rings stuff. I'm not sure exactly how that.
Is Tokyo still more popular than async standard?
It was around before, so a lot of people were used to using it, and they sort of moved the new syntax. But like in Node, where like Henry Ford or the Model T, you can have any color you want as long as it's black. There's only one runtime for everything, so people never had to worry about compatibility because it was a highly opinionated framework.
What's the Wi-Fi password?
Startup 01 or Startup 02?
Startup 01 or 2?
Yeah. Oh, share password, yes. Oh, well, I don't have to share it because you got it right.
Did I get it right?
You must have, because the share thing went away.
Can also
I noticed that before.
Or it could be just timed out because it was a while ago.
Well, hey, wait a minute.
Magic.
Well, if you make it come up again, then I will click the yes share.
It came up again because it didn't like it.
So, thus quoth the good book. This is actually not the good book. This is the lesser book. The good book.
I like the O'Reilly book better.
But, okay. Well, yeah, it's definitely, this one's
That's
got more
second
detail
edition,
to it.
right?
Yeah.
Okay.
Second edition. Got it under your recommendation. Actually, I don't remember if it was your recommendation.
so.
But
It probably was.
The last meetup.
I seconded the recommendation, just for that.
Yeah, so
Just for my-
what do the kids call it these days? Shilling? I'll shill this book. I'll put a Amazon link in the description.
Is that what it's-
I think my grandpa.
If you make a post on Reddit and you recommend something
I'll
to
take it
someone,
works.
they call it shilling.
Oh yeah. Yeah, Reddit. Yeah, they do that.
The orange side.
Yeah, it's like, well, so there. Oh, okay. I'm going to take a brief side tangent for no more than 1.5 minutes. So I figured out how to rip Blu-rays the easiest way possible. And there are mega threads that say, well, here's the 50 Blu-ray players that have ever worked with this method. And here's the 40 different firmwares that you can cross-flash between them. And I found, well, if you use exactly this Blu-ray player, which is the cheapest in its class for having the criteria that are necessary, and cheapest, most reliable, best value, let's call it best value. So if you get this one that is the best value, and you get this thing that is the best value, and you get this thing that is the best value, then you will be able to rip your Blu-rays without spending hours of your time or ripping out your hair. And so I posted that on Reddit, and then they gave me a bunch of flack. And it's like, you do realize that the alternative is that someone has to go through the mega thread and then buy some of these drives, and some of them will work and some of them won't, and some of them will get crapped out. Like, just let me post the answer that everyone actually wants. And it was one of those things where everybody upvoted it, but then it was removed for violating, for being unsafe for the community. It's like, seriously? Whatever.
Are there any other concurrency models you have on there?
I don't have any other concurrency models on here, but what I was going to quote from the book is use async standard task, net and task. And so you can use the version of net that is async standard, and you can use task instead of thread, and it looks almost identical to the thread example. So if you just go through your examples and replace net and thread with async standard, net, and task, everything should make you happy and feel glorious.
So that's probably an important point to call out. Async standard, that program's designed to look like the standard library as much as possible. So that's sort of the whole ideal behind it. And Tokyo is just like the first executor out there plowing forward, trying to figure it all out. So they just figured out and got it working first.
So it's been
And now
fairly successful idea.
Yeah,
They were,
Tokyo works really
They
well.
were very successful, and they did a lot of rewriting to make it with the new syntax, but still, I'm curious where it goes long term. Are you familiar with software transactional memory as a memory sharing mechanism?
No.
Clojure uses this to share memory.
Yeah.
It works like a distributed database in that if I have a distributed database and I have to do a lot of reads and writes, I've got the issue about potential conflict. And how do I do that without grabbing a mutex, which could lock everyone else out from using the system? What they do is that you take a snapshot of how things are, you have a transaction log, like a transaction to a database, to say, okay, I'm going to do these things. And then before you say commit, you go back and check the current state of the memory that you were dependent on. And if that has changed on you, you abort the transaction and start over again. But if it hasn't changed, then you can commit. So basically it's saying that, hey, I'm going to bet, rather than grabbing exclusive access, I'm going to bet that most of the time this stuff isn't going to be changing underneath me. And I can just take a copy and do what I want, but before I put the new value back in the table, I have to make sure someone else hasn't been changing that first, or else I have to start over. And it's neat. There's no need to do it in Rust. You can't use any other language, but for some reason in Clojure, that's the one they decided to go with.
What is the syntax like on that? Is there any special syntax to it, or is it just an under-the-hood copy-on-write type of thing?
It's been a while since I did Clojure. My memory is basically, they had atoms and things like, you're basically saying, here's this thing that I want to put my memory stuff into, and you sort of have to declare some sort of data structure around that to say, there's this stuff I want to share or do something with, and the operating system has a library that wraps around that to do the transactions and such. So you aren't directly accessing the variable. You have to have this variable wrapped in this library. It's been a few years, but it's exactly the same logic that you would use with a distributed database, where you have to do both reads and writes across a distributed system without getting inclusive blocks. That's where it comes from the same research.
Clojure is a dialect of Lisp. There's lots of parentheses.
On the JVM.
Implemented on the JVM.
Somebody on Twitter was mentioning, why don't we get people to learn functional languages more? And it was like, name a functional language that has a standard distribution that's easy to use. And they were like, not Lisp. But it sounds like maybe it is.
If you were asked the question, is Rust functional? It supports a functional paradigm, but one of the fundamental things about a functional language is supposed to have immutable data. And why is that important? Well, it's supposed to make things easy to reason about, easy to do concurrency, but you don't necessarily need immutable data all the time in Rust, because the borrow checker tells you when it's safe not to have mutable data.
Mm-hmm.
So in a way, it supports, but it sort of makes part of one of the axioms of functional programming not necessary.
Mm-hmm.
So yeah, I can do map reduce and all bunch of functional stuff, and I can interview whatever I want to, but I don't have to worry about the data sharing because the borrower checker didn't exist back then. And I was looking at just how big the Rust compiler is. If you tried creating the Rust compiler back in the 1990s, you would not have had enough memory in your system or enough computer time to compile anything. I mean, all that extra static checking to do, that has a price. You just could not do it back
I
then.
had a guy in one of my courses who had an old MacBook Air with 2 gigs of RAM. He couldn't compile any of our examples. I was so sad. It was just like,
Hello world.
he could do Hello World, but nothing significant. Because, with 2 gigs of RAM on a modern distribution, you've got like 0 available RAM.
Doesn't Rust give you the option to turn off a lot of flags?
Yeah, you probably could, but
you can turn off the optimizations.
it's in a tutorial, right?
Yeah, you can turn off the optimizations, which take more time, but the fundamental borrow checker to make sure that everything you do is thread safe and memory safe. They couldn't do that in C++ 20, 30 years ago because the compiler languages take forever. So if you're in C++ these days, there's a lot of vendors out there that sell tools that will go analyze your code and find things they think are wrong or dangerous to you, and there's a false positive those findings and so forth. And it's like, well, all that static analysis is just built into the Rust compiler. If it sees something that I can't guarantee is safe, sorry, you can't compile. And that I spent my first month bashing my head against that.
Yeah, I think that's the hard thing with Rust, is coming in as a very senior level engineer to not have something that like you pick up in a weekend, right?
Oh yeah.
I had to just go at work and was like, okay, I learned it in a day or two. And
Well,
put it in
that's
production.
part of the promise of Go. That is
Well,
one of the goals of Go, is that it is something you can learn in a weekend. That is
But even if you
explicit.
looked at it, any
But I
of the,
wonder-
like popular modern languages, right now.
Because I started with assembly language in C, and the guy who did Stack Overflow, forgetting his name,
Joel Spolsky.
thank you. He came up with a law called the law of leaky abstractions, which is we keep on making these things to make it easier for people to program and not worry about the messy details, but none of these abstractions are perfect to isolate you from all the bad stuff in all cases. So we reduce the amount of time it takes to be able to know the learning curve to get to where you can get something running, but we end up increasing the amount of time it takes for you to become an expert to be able to debug all the things that might come up in production. And so when I like Rust because I like understanding what it is, being that close. But if I'm using JavaScript, or if I'm using Python or using these other things, it's like, okay, am I going to be running into a case where to figure out what's going on, I need to figure out what's really going on in those libraries in isolation to go deal with the issue that I have to deal with. So, if Go successfully abstracts you from, or Node, whatever it is, abstracts you from all these things you have to worry about, hey, it's great. But I think there's a lot of times in the past, if I say, well, 99.9% of the time, yes, but that 0.1% of the time, no. And I've worked in medical devices and other things where you just absolutely have to guarantee that you know exactly what's going to happen and you're not going to have a problem. And I just really love the guarantees that Rust has, that if it compiles, yes, you can have logic bugs, but as far as all that other stuff about things working, it's pretty solid. Want to dance?
So do we have any questions?
How many people we got online? We got any regulars?
Yeah,
Any
at least 3
people?
online.
Let me check and see where the people online are. They're in this tab.
In the Jitsi
You
chat.
have a Ferris sticker?
Yeah.
Did you bring those last time?
Oh, gosh.
First ones are
He
new.
brought
Sorry, there
those.
was a whole
This is
ton
awesome.
of chat that went
So
on
we
here
stocked up
that
the
I just
holographic
missed.
ones and got some more Ferris ones. Or
Thank you.
made some Ferris ones.
Do you need any funds for this?
Funds would be nice.
So-
I don't know how.
Yeah.
It's-
I usually only go when they're on sale.
In the programming that I do, I have things that have to happen concurrently or in parallel, but I have only a small number of things I have to worry about at a time. So for ease of reasoning about what's going on, it's easier for me to set up a thread that just worries about monitoring and take care of that task. You take care of part of that part of the machine, I take care of part of that machine. I only have like 8 to 16 things to worry about. So I can afford the luxury of having my stack allocation and context switching per thread because I only have 8 to 16 of them at a time or something. But if I was doing a web server or telecommunication thing or whatever where I have 10,000 clients to deal with, then I would finally make myself learn how to do async await. I just haven't run into the need yet for what I need to do because for me, just with my background, it's easy for me to reason about well-divided tasks, well-divided threads to do that.
Yeah. I know what you're talking about.
How does Rust handle that? So if you're spawning new threads, but you're going to obviously have different numbers of threads depending on where you're deploying. How does it handle that if you deploy, you spawn a thread, then there's not a physical one available?
Well, the operating system will let you create new threads up to some large number.
Right.
So, do you want to explain the difference between a green thread and an OS thread?
Well, is it going to just handle queuing behind the scenes, or is it going to create a virtual
It's going to create.
thread?
Rust will, every time you say spawn, Rust will create an OS thread.
Okay.
And the OS just has to manage the bits of the hardware.
Whereas something like Go or Erlang, the green so-called green threads, is doing essentially the same thing that Node is. It's having a concurrent system where rather than allocating a completely separate thread and take the OS manage it, it's going to manage it in its own runtime. Where it'll allocate as many threads as the CPUs are for it to use, and just have a runtime for each one of those. And they're much faster, switching back and forth. But Rust, when you do a thread, are you familiar with the move semantics? So in order to make sure the borrow checker, to make sure you do something that are thread safe, it talks about if you're sharing something which is immutable, no problem. Everyone can share read-only something at the same time, no big deal. But if you have something which is going to mutate, there is syntax where I would say, hey, I'm going to move this, say, I'm transferring ownership of this into this other thread. So that thread's responsible for taking care of it. You can write to it, worry about when it's done, and delete the memory, but no one else in any other thread can access that. And that was another, so learning about the borrow checker, just general memory was one thing, and then you had to sort of learn extra level to go to the threads to realize that, hey, I have to make sure when I'm sharing things, I am sharing them either immutably, or I'm very clear about only this thread is got writable access to it.
So if you're programming for like something like a microcontroller, does it still have that concept of OS managed threads?
Depends on the OS for your microcontroller. If you're running on a bare machine, no.
It depends upon the OS. So if you're bare metal, no OS, you don't have threads. If you could, however, write your own runtime.
Yeah, I just mean if you did something like a black
and then
pill or
yourself.
something like that. Yeah.
So I do want to cover green threads versus OS threads, but
I think Daryl did a pretty good job of summarizing it.
okay. Yeah, I was just going to say I don't really know the difference that well because in different languages it means more different things. Like a green thread in Ruby or Python is not like a Go routine.
Yeah. The green threads are things which are not OS threads. It's some sort of runtime the language or library has come up with to manage concurrent programming. The different languages, because they have different limitations, have different rules about how that works. So yes, it's different in Erlang versus Go, but you are not spinning off an OS thread for every thread that you spin off in those languages.
So you have, your processor has 16 threads. OS has a bunch of, like, you can manage however many threads. And then you have root code, which is VM, runtime, manage.
I guess one thing we could talk about is preemptive versus non-preemptive.
CPU core cannot handle a thread.
Say that one more time.
Logical.
Another thing we could talk about is preemptive model versus non-preemptive models. So Rust, I guess, would be like cooperative, right? Because you have to yield cooperatively, whereas coroutines would be preemptive, as in the runtime can interrupt your task at any time.
Okay, so let me try to summarize that. So talking about preemptive versus non-preemptive and cooperative threads. Rust threads would be considered cooperative, whereas Go routines would be, what did you say they were?
So I wouldn't say Rust threads, I would say like async await or futures in Rust. I guess I would call them tasks, right? That's what that's what the literature calls them, tasks.
Yes.
So Rust tasks would be cooperative because every time you set up an await point, you're yielding, right? Yielding the CPU.
Okay.
Whereas in